Thank you very much for watching these videos. My name is Amir Keban Khandani and I am with the EC Department of University of Warwick. So I will present this work in the context of weak Gaussian interference channel because that's a topic that I've been of more interest, but the results are applicable to every value of crossing. It's critical that you please read this footnote before you starting reading this paper, and it explains how the problem has been simplified. The problem has been complex and more or less intractable because the capacity region of such a channel is known to include time sharing, meaning that for the values of power allocated to the user, you may get this curve. For another power, you get this different curve, and interpolation or time sharing between them, this straight line, is superior to both of them. This requires, deciding how many of those you need, which I call them phases, how you divide the power, and so on and so forth, which makes the problem very complex. So in this work, the issue of time sharing and power allocation is decomposed from the proof of Gaussianity, optimality of Gaussian distribution. And this is done by focusing on one of these curves at a time. And it will be shown that you need at most two such curves. So meaning the parameter Q in computing the so-called upper concave envelope is limited to 2. Over one phase, both users are active. Over another phase, if it exists, a single user is active, meaning that the channel over the second phase is a simple AWGN channel. Now, focusing on the A phase, that both users are active, the power is divided between public and private messages. We go through the boundary by reallocating the power between the two, increasing the power of one of the messages, you or we, at the cost of reducing the other. And the sum remains the same. The fact that the sum remains the same allows us to look at this optimization problem in a space continuous in terms of powers. And that's a key point that allows to show that Gaussian is optimal. Now, the way that in addition to showing that the phase that is both users are active, Gaussian is optimum, and indeed it will be shown that IID Gaussian codebooks are optimal, meaning that there is no need for vector coding. In order to show that we can cover the boundary in a continuous manner, the arguments are expressed in terms of starting from a point with maximum R1, which is known to be achieved with Gaussian, then moving counterclockwise through the boundary and showing that if at a point Gaussian is optimum in a recursive manner, when we look at the criteria expressed in terms of this length and this slope as a constraint optimization problem, then Gaussian distribution using calculus of variation is shown that they will be making the first order variation 0 and the second order variation is non-zero, meaning that we get either a local maximum or a local minimum. Then, some conditions are established that shows how this becomes the local maximum, and then conditions that how it becomes global maximum, and then showing that you can achieve the same value for the weighted sum rate by just limiting yourself to single letter. So vector is not needed. There is also another point that needs to be addressed is that by taking these steps, we are able to cover the entire boundary in a continuous and consistent manner. That is performed by showing what conditions putting some condition on the way these power reallocation vectors are essentially computed, or in, what do we do, what kind of condition we put on this power reallocation vector. And another thing is that a boundary is covered in small steps. Each step has its power reallocation vector that can satisfy the condition that I call Pareto condition for power reallocation. And another condition that we impose is that when you move from a point to, let's say, another point, and this is a very small step, we do this such that the strategy doesn't change. What it means, a strategy means that, for example, if user 1 has public and private, user 2 has public and private, it remains the same throughout the segment. If one of these messages, the power reaches to 0, it will be at the end of that segment. So throughout the segment, the number of messages, the way they are encoded, the way they are decoded, remains the same, only the power between them changes. And the change in the power between the two messages, meaning user 1, U1 and V1, user 2, U2 and V2, satisfy that Pareto optimality condition. Now, with this, also, let me just add one other point, that as we are moving, R1 reduces because we are moving in the lower part of the boundary, and R2 is increasing. So we compute R1 as the rate at this point minus the rate at this point. So it's indeed the negative of the change in the actual rate. And then consequently, both of these quantities will be positive. Optimality, instead of expressing it in terms of R1 plus mu R2, is expressed in terms of a constraint optimization, meaning that maximize R1 for a given R2 or vice versa, maximize gamma for a given epsilon and vice versa. Now, this also solved the issue that if you wanted to maximize R1 and plus mu R2 directly, as you make movements, mu also changes, the slope changes, and that would add another dimension to the complex. So please spend a few minutes and read this section, because that will give an overview of how these things are glued together. And in particular, there will be a section 4, which is limited to single letter codebooks. And then in section 4, it's all limited to single letter, will be shown what is the best you can do. And then in another section, it gets into vector encoding, shows that the vector encoding is not needed. So you can achieve the same value of the weighted sum rate just by using single letter. And in the same section, chapter 5 or section 5, it will be shown that you don't need vectors and so on and so forth, and you need only 2 phases, as I mentioned. With this, I go to next